name is Rob Rallo. I'm a senior engineer with SunWize Power Battery, and let me start by getting some of the fine print out of the way. This webinar will be recorded, and it will be available online shortly after we're done, so you can go back and review it if you like. Also, everyone is muted, as we do have quite a few people on this webinar. If you have any questions, please type them in the box. Okay, thank you. I'm going to start by giving a little background on myself and on SunWize. I have been in the industry for over 25 years, mostly in the standalone off-grid battery industry. SunWize Power Battery has been in the off-grid business for about 20 plus years with installations all around the world. We're focused on standalone systems, hybrid battery backup, and pretty much any battery-based business, anything that's in a remote power-sensitive application. We have manufacturing and sales offices throughout the United States. And we provide, as I mentioned before, we provide standalone systems, hybrid systems, battery backup, as well as battery backup grid tie. We also provide services such as help with technical specifications, consulting, design and engineering, integration, documentation, and of course providing either components or integrated power solutions. So today's topic is types of charge controllers. The basic function of a charge controller is to prevent the battery from being overcharged, undercharged. For today's discussion, we're going to focus primarily on the types of charge controllers and how they operate. I'm not going to really get into the features of them, like for instance low voltage disconnects or alarms, meters and things like that, or even into set points. Those could be a discussion or topic for another day. So today we're going to focus on just the types of charge controllers and how they operate. The reason for that is that it's very important to understand how a charge controller operates in order to best be able to understand how it works and then whether it's functioning correctly or not. You also know what type of charge controller you have and to understand how to properly size it. Different charge controllers operate differently and therefore have to be sized differently to the solar array. Along with that, just a side note, I'm always surprised at the number of technical support calls we get where people have said that their charge controllers have failed, and the majority of those really hasn't been the charge controller. It's been something else in the system, either a problem with the solar array or an old battery or a load is too big for the system or something like that. That being said, again, understanding how your charge controller works will help you to troubleshoot your system better. And as the charge controller generally is a central point in the system, it's also a good place to start with the troubleshooting. Now, although it may not be the most expensive part of your system, it can help to protect the most expensive part of your system, your batteries. Again, it's there to prevent your batteries from being overcharged, undercharged. The batteries are probably one of the most expensive components in your systems. They should last 5 or more years. However, if there is a problem with the system, that battery may last a lot less and you've wasted money. So it's important to understand that your charge controller is working correctly in order to protect the investment in your system. That being said, one of the most important features of a charge controller, although I still will not mention them, I will mention one, temperature compensation. It really should be there. It's very important to have that. The battery voltage should be adjusted for that. In other words, when it's cold out, the battery will be charged more. When it's warm out, it will be charged less. If you do not have that, your battery will not get properly charged, and it could fail prematurely. Okay? There are 4 basic types of charge controllers. We have the shunt regulator, series regulator, pulse width modulated regulator, and maximum power point trackers. And they're pretty much listed in chronological order of which they came out as well, by the way. So we're going to start that way as well. Let's see, I mentioned, already talked about some of this. What do we need to know about this stuff? Again, in order to size it correctly, how they work, and to help you troubleshoot it better. So let's start with the shunt regulator. Shunt regulators are one of the older technologies that's been around since the 80s. And although it is an older technology, it still works quite well. They are still used today. They have, some of them have Class 1 DIP certifications. They're used quite a bit in the oil and gas industry. They function by short-circuiting the solar array when a battery reaches a set voltage. Okay, so what happens is it literally shorts the entire array, converting the array to 0 volts basically, and stopping the current from flowing to the batteries. When that happens, the battery then, because it has no more charge voltage, will then start discharging the load, and the battery voltage will drop. When the battery voltage drops, it will reach a reconnect point. Then the array is unshorted, allowing current to flow to the battery again. Okay, so shunt regulators are generally, because they're generally solid state and they contain a blocking diode. The blocking diode is very important as it prevents that battery from being shorted as well when the array is shorted. So they put a blocking diode line to prevent that battery from being discharged into the array, into that short circuiting mechanism. And a transistor is typically used for that short circuiting. However, a relay can be used as well. Shunt regulators are generally used in negatively grounded systems. Primarily because of the blocking diode and the circuitry involved, although you theoretically could design and build one for positive ground. I am not aware of any at this time. Okay, since the shunt regulators basically disconnect the entire array from the battery when it reaches a voltage and then reconnects when that voltage drops back down, they're typically referred to as an on-off type charge controller. It's either on or off. The battery either receives a full voltage from the array or none at all. Okay, so what'll happen, as I mentioned before, what'll happen is the battery voltage will rise up as the charge is there, the array will be short-circuited, and then as that voltage drops down, it'll get reconnected. And these cycles, so I'll just repeat the cycle, these cycles can range anywhere from minutes to seconds depending upon the state of charge of the battery, how big the load is to drain the battery back down, the sunlight available, and temperature, and many other factors too. Okay, this type of charge regimen is sometimes referred to as a pulse regulator or pulse charge of the batteries. And again, it's a one-stage charge controller. We'll be talking about multi-stage ones later, but right now this is strictly a one-stage. In other words, it's either on or off. There's only one stage to it. Okay. And again, although this may not sound like a very sophisticated charge controller, it isn't. They're out there. They've been around for a very long time, and they are quite reliable, so a lot of people do like them. An example of a shunt regulator that's still being used today is the Specialty Concepts ASC regulator. And you'll notice it is a rather small regulator. Generally, shunt regulators are small. That is because you're having to shunt a lot of current from a solar array. There's a lot of current involved, so you do not want to do this with a large solar array. They're generally used with just 1 or 2 modules, and they do come in 12 and 24 volts. But again, they're generally used with smaller arrays, just 1 or 2 modules types of things. Also, they can get hot because of the transistors and the blocking diode, and they're keeping in mind you have the full array current going through this unit when you are shunting. And this kind of gives you a little diagram of it. You can see the solar array and the battery. In parallel, you got a blocking diode there again, preventing the battery from discharging into the solar array. And there's the shunting element, which is typically a transistor in this case, short-circuiting the solar module. So in again in the late 80s, early 90s, series regulators came into play. And the series regulator kind of works the opposite of the shunt regulator. It actually open circuits the array when you reach the voltage. You still have this on voltage, off voltage, but instead of short circuiting, you're going to open circuit it. So most of the series regulators, although they can use transistors, most of those are using relays, and that made it so that you could put the relay in either the positive or a negative line, making these more readily available for positive and negatively grounded systems. Again, because they do have that array disconnect voltage and the reconnect voltage, and the solar array is typically an on-off type. And because of that, you're going to have that pulse charge mechanism once again. Now, what you can do is with these series regulators you can put multiple relays in parallel with them. So you can get a multi-stage unit and step the charge current to the battery. Unlike the shunt regulator where you're shunting the entire array, So you can only get that one stage. Because of the series regulator, you can put multiple relays in parallel, and you can stagger them or step them so they have different, depending upon the logic being used, so that you can disconnect those relays and reconnect them at various voltages, allowing you to taper or step, more like a step, because again, you have various levels of current that you can drop to the battery. The number of steps you have depends upon the number of relays you have. So if you have 2 relays, you can do 2 steps. You have 3 relays, you can do 3 steps, or 3 stages. Now, series regulators are used frequently with very large systems for this reason. Although there's a lot of current flow through the relays, there's not a lot of heat dissipation. There aren't diodes and transistors and other devices that are going to be dropping voltage or energy. So they're also very efficient units as well. So they're used with very large systems. They run much cooler. They can also be packaged in smaller enclosures because of this. Now, also, because and you can add, again, as many relays as you need to, depending upon the logic involved, to get to big arrays. Example of a series regulator frequently still used today is the digital solar MPR controller, and it uses mercury displacement relays. One of the things about the relays are that, going back to the shunt regulator and this pulse charging methodology, you can have, again, cycles of ranging anywhere from minutes to seconds, which means you could cycle that relay very frequently. Most mechanical relays would fail rather quickly because of that, but mercury displacement relays are rated to millions of cycles and can typically last 10 to 20 years in a solar application. So you'll frequently find these series regulators will use MDRs, the mercury displacement relays, for that. And here's a photo of an MPR controller. This one has two relays in it, so it's a two-step or two-stage unit. And all of this unit, you can get up to 200 amps in this small package, which is in roughly 16 inches by 14 inches, and it comes in a NEMA 4X fiberglass enclosure. So it's again, a compact package for a lot of current, making them very suitable to very large solar systems. And this is what happens when you try to do it with an MPPT or PWM type one. You end up having a whole line of these, and you can see the giant fins that have to heat sink all of that energy if you were to try to do it with some of the other types. So this works fine. You can do this, but again, this is actually ended up being put inside a giant container because of that. And again, you have to get the heat out of that container because it's going to generate a lot. So just something to consider when you're looking at what type of charge control you might want to use for your application and why you might want to use one type over the other. And here is a diagram, a simple diagram of a series regulator. Again, you will notice that it's very simple. You just have the solar module in parallel with the battery, and then you will just either open or close that relay or transistor. Again, this can be done with a transistor, and I'll talk about that in just a minute with the pulse width modulating units. But again, just open or closes, and again, you can have multiple of those in parallel depending upon the type of controller you have and how large your solar array is. The other thing to notice about this is that because this is open, when the regulator is regulating, that array voltage will go to open circuit voltage, which means if you have a 12-volt system, that array voltage will be about 20 volts. So if you're going to check your system and you're checking your array voltage, all of a sudden you see it's at 20 volts, you might think there's a problem with your system when there really isn't. Your system may actually be functioning correctly. You just need to check the state of charge of your battery. If your battery is at a full state of charge, you can check that with the voltage. Say your battery's at 14 volts. Then you will realize that the system is working correctly, that your array has been disconnected because your battery's at a full state of charge, and it is seeing open circuit voltage. The opposite will be true of a shunt regulator, and this is, again, the reason you need to know what type of regulator you have. If you have a shunt regulator and you're reading 0 volts in your solar array and your battery is at a full state of charge, then you will realize that everything is functioning correctly. So if you're checking voltages in a solar array and you're finding that they could be 0 or open circuit or something like that, you need to know what type of charge control you're working with and whether it's regulating or not, whether your battery's at a full state of charge, in order to understand whether it's working properly and whether there's really a problem with your system or it's functioning as it should be. So the next evolution from the shunt to the series to now the pulse width modulator regulator. Basically, the pulse width modulator regulator takes a series regulator and adds a transistor to it and that series line. And what it does is it'll switch that transistor to high frequency. I remember I mentioned the pulses were anywhere from minutes to seconds. Well, these transistors operate usually in the kilohertz range, very fast. And by modulating the width of that, to the transistor, they're able to maintain a constant voltage. Instead of having a disconnect voltage and a reconnect voltage, as other units have, you can now have a charge voltage and a float voltage, or even an absorption cycle. And we'll get into that in just a minute. So when the width is at 100%, that transistor is full on, allowing the full current from the solar array to bulk charge the battery. And then when the width of that modulation is at 0, the transistor is full off. So if you have 100% transistor, it's full on. If you've got 0, then it's full off. Now that would kind of be consistent with the on-off type. However, when you vary, by varying that pulse width, that's how you can create a constant voltage out. And I'll have a chart on that in just a minute. But I do want to also mention, like the series regulator, because of the fact that that transistor can be put in either the positive or negative line, you can use it in both positive and negative grounded systems. Now, unlike the relays that you can easily move because they're outside of the circuitry, in this case, since the transistor is usually built into a unit, that regulator has to be built for that. So you would have to check with the manufacturers whether they have a positive ground version or not. Okay, as I mentioned, you would vary that width in order to create that constant voltage. Okay. Now, one thing to consider with that frequency is if you have a sensitive load, perhaps radios and other equipment, that can be an issue with that. A lot of the pulse width modulated regulators have an option to disable the pulse width modulator feature and convert it back into a straight series regulator with just an on-off type of regulation. Some of them may be a jumper you have to remove, or there may be a software programming setting for it. So if you do find you have an issue with noise on your load, you may want to look at what type of charge controller you have, and if you have a pulse width modulated one, you may want to think about perhaps disabling that feature and see if your problem goes away. Now, since it can create a constant voltage, a regulator can be a multi-stage unit. So generally, as I mentioned, you have that 100% full-on bulk charging the battery with all the current you have, and then once that battery gets to the full state of charge, it'll start holding and maintaining that voltage through an absorption cycle, and then eventually it will get to a float cycle once it's gone through absorption. Generally, in a solar power system, you're going to rarely get to the float. Usually, in a good day, you'll get to absorption, and then that's usually about it. I think the only time we're going to see a float setting is probably at the end of the day in the summer with some good sunlight out. And since pulse width modulation regulators require that pulse width modulation transistor, they're always solid state. An example of some PWM regulators we have here are the Focus Dingo. We've got a Morningstar TriStar. We've got Steka, Midnight Solar, and many, many others. Outback Power. There are many, many, many companies that make pulse width modulated regulators. Similar to the shunt regulator, though, because they are solid state, there is a heat dissipation with them, and you have to take that into account when working with them if you have many inside a sealed enclosure. And I would refer you back to that photo we showed earlier with multiple controllers together in a line and parallel, and all those heat sinks. So you do have to consider that with a regulator, with the pulse width modulated regulator. Again, if you've only got one or two, it may not be an issue. If you've got multiple ones, that heat generated could be a problem. And here's the simple diagram of the PWM regulator. Again, you're looking at that this is exactly the same as a series, other than you've replaced a relay with a transistor, and then you're sending it a waveform. And we're going to share that waveform in just a second. Here's kind of an example of that waveform, and this is important to understand with the pulse width modulation. And I'd like to thank my friends at Focus for letting me use this for this presentation. This shows a 70% duty cycle. So basically, you have a 70% wave and a 30% off. So you have 70% on, 30% off. So by adjusting this, that waveform somewhere between 0 and 100, as I mentioned before, again, this is showing a 70-30, this is how you can maintain that constant voltage to the battery. Now, it's important to understand that you're still seeing that as far as the controller is concerned, it's still seeing full array current. You have basically that width is going from the full current to 0 and then back up to full current again. It's just doing it really, really fast, unlike the series regulator. So in terms of the controller, though, it's thinking full current, so you have to size it that way, and we'll talk about that more in size, but it's important to understand that it has to be sized with a full current because it's going to see it with this wave. Even when it goes to 0, you're going to go back up to full. Now, on the other hand, though, because this is happening so quickly, the battery's not really seeing it. If you think about it on an average, because you have 70% on, 30% off, the battery's not going to see the full current, but maybe about 70% of that current instead, and that's how you maintain that constant voltage, because of that average going on. The other thing to think about with this is, getting back to troubleshooting, it's very difficult to troubleshoot these because that solar array could be anywhere between the battery voltage when it is bulk charging, when you have that full on, to it could be open circuit voltage when the battery is fully charged and it is disconnected to stop the charging, and anywhere in between. So again, going back to the 12-volt system, your fully charged battery could be at 14 volts, and your array could be anywhere between there and 20 volts, depending upon the state of charge of the battery and where it is in the pulse width modulation and the percentage of duty cycle. So if you see your array somewhere around 16 volts or 18 volts, then you're probably in regulation, and you may want to just look at the charge controller and your battery voltage and see if that's the case. And if it is, then you know things are functioning correctly. So the next evolution was to take, since you've got the transistors in there, you've got pulse width modulation now going on, and now you've got some logic and circuitry. The next thing to do is to add even some more additional circuitry and logic in there and some additional smarts to it, and add in a little bit of additional hardware in terms of some type of some capacitors and maybe an inductor or something like that, so you can store a little bit of energy. And now you have a maximum power point tracker. These are a great improvement to the pulse width modulation in the sense that now the array voltage can vary from the battery voltage. So before, all these other units, the array voltage dependent upon regulation and the battery voltage. This is no longer true now. Now the array could be at a completely different voltage than the battery voltage at any stage of the battery charging cycle. And by doing this, the charge controller can then maximize the output from the solar array. So these allow you to maximize every watt from the solar array going to the battery and not have to worry about the current. And this will come up when we start talking about how to actually size the charge controllers. Now, generally, there still needs to be a reference voltage a charge controller works with, so generally the negative line will be common in these systems, so you need to be aware of that. There are ways in which you can use them in positive ground systems, but it's very tricky because you're switching the grounded line. So I would suggest consulting us if you have an application like that, because they're generally designed to go in negative ground systems. Similar to pulse width modulated controllers, because they can control the charge current and voltage going to the battery, you can create a multi-stage charger with bulk absorption and float settings. And also, they're always solid state because that they require transistors in order to do this. And because of that, and even more so than the pulse width modulated controllers, because of the additional circuitry in there to store energy, they're going to run even hotter than the PWM charge controllers. You'll notice if you ever look at a PWM controller and an MPPT side by side, for the same amount of current, you'll notice that it has a quite a bit larger heat sink, and that is because of that. So it has to dissipate even more heat out of the unit, and you might want to think about that when you're working again with a large solar system, that you have additional heat to deal with, and you have these large controllers that you need to install somewhere. And just a few examples of maximum point tracker power point trackers. We're showing here an Outback FM60 or FM80. You've got the Morningstar TriStars. They come in 45 and 60 amps. You've got a Steca, and we've got Focus. Focus has got several MPPT options as well. And here's the simple diagram for it. You can see I'm pretty much just showing that as a black box because it pretty much is. There's a lot that goes on inside of these units. It's not just a simple switching of a transistor. There's more going on than that. You've got, again, some stored energy components and other devices in there, so there's a lot going on inside these devices. So now moving on to the how do we size charge controllers. And again, this is dependent upon the type you have, whether it's a shunt, series, PWM, or MPPT. You'll notice because the shunt, series, and PWM regulators are all pretty much current-based, they're sending the maximum rate current through or less than that, depending upon whether it's depending on the state of charge of the battery. Because of that, the sizing methodology for those would be mostly current-based. The MPPT is a little bit different because it's trying to maximize the wattage or the power from the solar array, so that one's going to be sized more based upon power and not based upon current. Excuse me. So, for a shunt regulator, again, because you're short-circuiting the solar array, you need the size for that. You need the size for that maximum current. Okay, then NEC says you should also add an additional 25% for cloud enhancement, and then an additional 25% for safety margin. So what ends up happening is you end up taking the short circuit current times 1.56, and that 1.56 is the 25% for cloud enhancement plus the 25% for safety margin. The overcurrent protection, which can either be a fuse or a circuit breaker, should be sized in a similar manner for the same reason. You don't want that to trip accidentally, but you do want it there to protect the system. So, series regulators, the same thing. Whether you have, whether it's a transistor-based or it is a relay-based, either way, you have the same thing. You've got that maximum current from the solar array. So again, you're going to want to take that short circuit current, the maximum current, add 25% for cloud enhancement, and then 25% for safety margin. And your overcurrent protection will be sized the same way per NEC. Same thing with the pulse width modulators. Again, when you go back to that that chart I showed you on the waveform, you'll see that you do get that maximum current, so you need the size for that. Sometimes this is a mistake and people don't realize that. And depending upon the pulse width modulator regulator have, several things can happen. This is true for any of these current-based regulators, actually. If you overload them, they could melt down. Literally, the transistors could burn up, and things could happen to them. Some of the newer pulse width modulated regulators will have a little bit of sophistication in it. They realize they're in an overload situation, and they may just shut down. Either way is not a good situation for your system. If the regulator burns up, that's not good. Things could catch on fire, and most likely your system will go down. And even if that doesn't happen because you have some circuitry that shuts down because of an overload situation, that still means your system's offline, and that means you'll probably lose the load. So in all of these situations, it's very important to size your regulator correctly so that you do have reliability for your system. You don't want to kind of cut things close and accidentally have it melt down. The other thing is that transistors don't like to run hot, so if you've sized your system kind of in a gray zone, you're running it kind of at its maximum, then you'll find that your regulator may not last quite as long. Most of these regulators have got 2 5-year warranties, sometimes even, and they have up to even a 10-year design life depending upon the model and the manufacturer. But that design life can be reduced dramatically by running it at its maximum all the time. So just something to consider when you're sizing your regulator, that it may be just a few dollars for the next size up, and it may end up extending the life of your regulator, so it may be worth the extra money to do that. And again, the overcurrent protection should be sized the same way. Okay, maximum power point trackers. Again, as I said before, very different because it is power-based. Also, because they can control that maximum power point, it can shift it. you can actually overload these units. These are the one exception to the rule that you can overload them. And sometimes that's not necessarily a bad thing to overload them. You don't want to do it on a regular basis, again, because if you run at its maximum, those transistors run hot. You could shorten its life. But having it run, say, in the middle of the summer or something like that, occasionally, that's not necessarily a problem. You just don't want to do it all the time. What will happen is that when they do reach the maximum, they will, as I said, they will adjust that point to limit the array. So we'll actually limit the output of the array to whatever the output of the unit is. So it'll automatically limit itself to its rated power or to its rated current output. The only problem with it is that the other problem with it is you may end up wasting the solar array power. So if you're always regulating that, if you're always kind of clipping the solar array, then you just wasted power. So another reason maybe not to design it so close to the edge. But if you have to, for some reason, you've oversized it for 10% extra or something like that, it's not a problem. The unit will not be damaged. So that being said, generally I try to size mine based upon the maximum of the array. So let's say, for instance, an example, I have a 600 watt solar array and I have a 12 volt battery. I will just divide the 600 by 12 volts, and I have about 50 amps. I would use a unit close to that, so I might use a 60 amp unit. Again, that 60 amp is on the battery side. So if you want to figure out how much array wattage is, let's say you have a 60 amp unit times 12 volts. That means it can really take about a 720 watt solar array. Again, you can oversize a little bit. It's not going to hurt anything. But again, you may not get, you may clip the wattage on the solar array and maybe not get the maximum out of it sometimes. So that's how you would size that. Again, you want to size it based upon the wattage of the array and the current output of the unit. Now, because of that, because the regulators, the maximum power point track regulators, can actually restrict the current on the output, there's a different way to do the overcurrent protection. There's actually a little exception in the NEC code, and I've put it up on the screen for you, that allows you to use a circuit breaker rated for that. So if you have a circuit breaker, going back to the 60 amp example I mentioned earlier, you can use a 60 amp circuit breaker with this, assuming the 60 amp is designed to operate at 100%. So if you have a circuit breaker that can do 60 amps at 100%, then you can actually use a 60 amp circuit breaker on a 60 amp charge regulator. Okay, because of that exception. That was actually put in mostly for the battery backup grid tie industry. Ones that might work with your Outback power unit or your Schneider Electric stuff, they had this clause put in the NEC code that allowed them to use 60 amp breakers and 60 amp charge controllers for that. So let me go ahead and take any questions at this time if there are any. Please feel free to type them in the chat box. And while that's going on, let's do a little poll, just out of curiosity, to see what type of charge regulators you are presently using in your systems. Okay, I think most of the people have voted. It looks like the majority are using either pulse width modulation or maximum power point tracking. Actually, almost 75% of you are using MPPT charge controllers. And a few are using the shunt, very few are using the series, but mostly pulse width modulated and MPPT. Okay. I see we have a question with regards to the, let's take a look here.
Yeah, I see a question on emailing out the slides. There's going to be a follow-up email that'll be sent to all attendees with the link on our website where this entire webinar will be uploaded, including all audio questions, everything else.
Okay. Since we do have a few more minutes left and not too many questions, we could as Errol mentioned, we do have some slides also available for you. We could talk a little bit more about maximum power point trackers versus PWMs if you like. And just briefly talk about that. And I'm going to send out a poll just to see how much extra energy you think you're going to get out of a maximum power point tracker versus a PWM. Okay, looks like most everybody had, oh, just a few more people are still voting. Okay, I think that's most everybody. Looks like the majority of the people think you're going to get between 15 and 20%. The reality is you get between approximately 3 and 8%. So if you picked 5 to 10%, you're probably you're fairly accurate. I know that's not much, and when you look at the expense of those, you may question whether they're worth it or not. And that's a topic for another day, perhaps. But the reason it's only 3 to 8% is because that wattage we mentioned before, that diminishes greatly with temperature. So in a hot climate on a hot day, you're only going to get about 3% extra out of it. And a colder climate on a cold day, you might get up to 8. Now, if you are in a cold climate and you need a little extra for the winter to get through the winter, that extra 8% may be worth it to you. It may not be worth it for that extra 8%, for the extra cost of the maximum power point tracker. It might be cheaper to add another module. Since the cost of solar has come down dramatically over the years, the need for a maximum power point tracker just to get a little extra out of the solar array seems to not really justify the additional cost. Now, there might be other reasons you might want to use a maximum power point tracker. You might want to use it because it works with your inverter or something like that. You might want to use it because you have voltage drop issues. You want to run your array at a higher voltage. So other good reasons to use it. But if it's to try to get extra out of the solar array, again, you're going to be between 3 and 8%, and that depends upon the operating temperature you're at that time. We will be coming out with a white paper on that soon that will show you the calculations so you can better understand how that works and why that works that way. And Errol and I are working on that, and hopefully we'll have that out within the next week or two.
Rob, I got a question here from somebody about voltage limits on charge controllers. For instance, if a charge controller has a maximum voltage of 50 volts or 60 volts, whatever, is that a hard limit, or is that something that you're able to go above by a small amount?
That's a very good question. It depends on the charge controller. Most manufacturers, that is a hard limit, and you want to make certain that your open circuit voltage of your solar array is limited to that. So it's very important to keep that in mind. I know I talked more about sizing for current. So you do want to keep that in mind. That's more going to come into play, I think, with the maximum power point trackers. And actually, that might lead to another discussion here in just a minute. For the other units, that array should always be sized to your battery. And again, because the solar array is connected directly to the battery. So if you're using a 24-volt module on a 12-volt battery with a PWM charge controller, all you're going to get out of it is the current out of it. You've pretty much wasted half its power or half its energy because that's being wasted in voltage. So you're going to want to size that solar module accordingly. So generally, for a 12-volt system, you're going to have a 20-volt solar module, open circuit voltage for a 24-volt, a 40-volt, and for a 48-volt and 80-volt open circuit voltage. Again, this is when working with either a shunt regulator or a series or a PWM. That module should be sized to charge the battery correctly. Now, for a pulse width modulated unit, it's different because, again, you are sizing based upon wattage. So there you can do all kinds of things. And most of those are rated anywhere between 80 volts maximum to 150, depending upon the unit you have. And most of those manufacturers are going to have some type of sizing chart on their website to help you with that. But you want to be very careful. Again, if you exceed that voltage on most of these units, There are overcurrent protection inside them, transorbs, resistors, things like that, that will pretty much melt down and the unit will become unusable at that point. So you want to make certain that you stay within those voltages. Now, what that brings up is, as I was mentioning, you want to make certain you use the correct solar module for charging your battery, and that brings up another question, another poll that I think we'll do real fast with regards to that. And I know a lot of people like to use 60 cell modules, and we pull up that one. A lot of people use 60 cell modules for charging 24-volt systems, and just want to real fast see how many people think that's okay or not. See, about 25% have voted. Okay, most people have voted. Okay. Yes, you can. That is correct. You can use a 60 cell 24-volt module. That's what you use with an MPPT charge controller. You cannot use it with the. You cannot use it to charge a 24-volt battery bank, but you can use it to charge a 12-volt battery bank. And the reason for that is that, again, that maximum power point tracker will try to extract as much energy out of it as it can. It's going to step that voltage down. So it's going to go ahead and take that wattage. It's going to convert it down to whatever it needs to charge that 24-volt battery bank. Now, the pulse width modulating unit will not. Now, you can actually use a 60 cell 24 module on a 24-volt battery bank with the PWM regulator. But you have to be very careful with that voltage you mentioned earlier. Just make sure you're not exceeding the maximum input voltage in the unit. But the other problem is you've also wasted that power. All that extra voltage that you have is not going to be used because you're only charging with the current. So it's very important when using the series of shunt or the PWM regulators to be looking at the charge current from the solar array, because that's what you're actually using to charge your battery with. And that'll actually make your system more cost effective that way.
Rob, we got another question sort of related to this. Could you speak a little bit about some of the guidelines regarding power production in general for the 4 different types? Are you going to get any more or less power for series and shunt regulators compared to PWM in that regard?
Good question. No, they're all about the same. Pretty much they all just pass current through to the battery. Some of them may have slightly different efficiencies, just a little bit of losses, but we're talking about 1%, which is pretty minimal, I think, when you're looking at the overall system itself. So they're all pretty much about the same, again, because they're all just passing current through to charge the battery. Where they really differ is in how they regulate. So once that battery reaches its full state of charge, how does it regulate its output to keep the battery from being overcharged or undercharged at that point? So that's where they really differ. But in terms of energy through, they're all pretty much the same. They're all pretty much going to bulk charge the battery until they reach a certain point, and then they're going to restrict that or eliminate that current to keep the battery at full state of charge. Obviously, the pulse width modulator is completely different, as we mentioned before. It will get you an extra 3 to 8% out, somewhere in that range. But in terms of the other types, doesn't matter at all. Pretty much about the same.
All right, Rob, we got one more question regarding Class 1 Division 2 solar charge controllers. Are there any solar charge controllers not rated or recommended for C1D2? I think the answer for that is that if you're using a controller in a C1D2 rated area, that you want to make sure specifically that it has that rated certification on the data sheet or wherever else. That's correct. And generally, they're going to be a solid state type. You don't want mechanical devices operating in that type of environment. So you will not find a series regulator actually certified for that.
There are a couple of brands that are. The ones I'm mostly aware of are either the Shunt regulator, the ASC that I mentioned earlier is certified for that, and I know that the Morningstar SunSaver is also, the pulse modulated unit, is also certified for Class 1 Div 2. And again, that's because they're solid state, and you also notice they're also smaller units. Again, they're because of the heat dissipation. You won't find the maximum power point trackers are certified for that, and that's because of the storage energy inside of them to do the MPPT, and also because of the heat dissipation. So they become a possible safety hazard, as well as the series type because of the mechanical nature of the relay. So those two, I'm not aware of any, and I doubt anybody would try to get one of those certified, those two types, but either the Shunt or PWM could be, and generally the ones that are one of those two types.
All right, Rob, we got one more question on how to quickly best evaluate whether the best choice is a PWM or an MPPT, given that roughly 3 to 8% increase in power and the price differential between the two. What do you think about the best way to evaluate that decision?
It also depends upon how big your system is and whether it's cheaper to add a little bit extra solar. So that's actually kind of a it depends question. It depends on a whole lot of things. It also depends on whether you are worried about a voltage drop issue. Again, if you've got an array that's away from the battery, you may want to run that array at a higher voltage and step it down so you have less output cable, so you can save some money there. But if you're just trying to do it for extra power production, it's most likely going to be cheaper to just go to a slightly bigger module or add another one depending upon how big your system is. Generally, there are going to be some exceptions to that, so that's one of those that might be application specific, and you may want to talk to your salesperson or whoever you're working with regards to your system sizing for that. Okay, any other questions?
Yeah, we got a couple more. We had a question on isolating the solar panel from the charge controller using a fuse or a breaker. Is it ever recommended, or does that have any uses?
Good question. It depends. If you have multiple modules in parallel, yes, they are needed. They're required by NEC, and that's a whole other topic in discussion of when do you need it, not with regards to that. So if you have multiple modules or strings in parallel, you most likely will require those for various reasons. If it is a single module or a single output, a single string, you may not. Generally, you do not need it there as long as you have a fuse or circuit breaker at the battery. A lot of these solid-state charge controllers will prevent that backfeeding so that they will prevent any type of short circuit from getting through anyway. If you were to short circuit those lines, the transistor or diode is going to block that from happening. So you don't really technically need one. Now, that being said, there are a lot of people that put them in anyway, and I always laugh. They just end up becoming glorified switches, and that's not necessarily a bad thing. It might be nice to have a circuit breaker there as a disconnect mechanism for troubleshooting your array, for doing your short circuit current test, your open circuit voltage, or something like that. May not be a bad idea to have one in there just for that purpose.
All right, we got one more question on how MPPTs versus PWMs may affect the health or longevity of a battery life. Are MPPTs going to necessarily result in a better performing or longer lasting battery compared to PWM?
No difference whatsoever. They both actually use very similar charge methodologies and algorithms, so they still have that absorption and that float voltage setting. So if you look at a charge algorithm for either one of those, they're very similar, almost identical. So there'll be no difference whatsoever.
All right, I think those are most of the questions that we have so far. If there's anything else, there's contact information where you can email us, as well as note that we'll send out the link to view this recorded webinar afterwards.
And I'm going to send out one last poll. I'm just curious, how useful was this webinar to everybody? Okay, looks like most people voted, and it looks like the majority of you thought it was quite useful. So thank you for your time, and we'll be having more of these webinars on other topics. If you can think of topics that might be useful to you, what questions you might have, things you might want to know more about, feel free to contact us, and we'd be happy to try to put together a webinar on that. So if there are no other questions, thank you for your time. I hope it was useful for most of you, as it looks like it was according to the poll. And again, this is recorded, and it will be up on website. We'll send you a link to that shortly in case you want to review any of the information or look at the slides once again. Thank you for your time.